Hello, we're going to finish up our discussion of linear algebra and matrices, looking at least squares and doing linear fits. And so the idea here is that you have a number of data points, x and y values. So maybe you have the point 1, 2, and the point 2, 7, 3, 9, 6, 5, whatever. Okay, so you have a whole bunch of data points, x and y values. And we also have a set of functions. So maybe our first function of x is just a linear function. And our second function of x is x squared. Maybe our third function of x, cosine of x. These can be whatever functions you want. They don't have to be polynomials. A lot of times you do this with polynomials. You have, and actually a very important possibility here is 1. So if you use 1 and various powers of x, so x squared, x cubed, etc., you're doing a polynomial fit. But this technique is not limited to polynomial fits. And what I want to do is I want to find the set of values such that I want it so that how about we call it, well, okay, yeah, I'll go with a's here. A times f1 of x plus b times f2 of x plus c times f3 of x for a given x. I want that to be as close as possible to the associated y. So if I plug in a 1 here, I want a value that's close to 2. If I plug in 2, I want a value that's close to 7. Now generally when you're doing this case, since I have 4 points and 4 functions here, it's quite possible that I actually could get these exactly equal. But generally when you're doing this, you have a lot more data points than you have functions. So I might only have 4 functions, but I might have 400 data points. So in that situation, it's not possible to get these to be equal. Instead, what I want to do is I want to minimize the difference of this. So I'm going to call this sum here with these different coefficients, I'm going to call that a capital F of x. So x is equal to the sum of, and we'll, instead of calling these a, b, c, I'm just going to call them different c values. C sub I times f sub I of x. Oops, I hit a superscript there. Okay, and I want to say that what I want is I want my f of x minus y for each sub I that we have here. This is our error. The ith error term. And I want to minimize that. Okay? And so what we'll do with a least squares fit is we're actually going to minimize the sum of the squares of the errors. Okay? That by making them squares, you make it so that you are less tolerant to large errors. So you want to try to make it so there are no large errors in this. And the question is, well, how do we do this? Well, this f function here is a sum over a whole bunch of terms. And we have a whole bunch of different x, y combinations here. So we can actually turn this, we're going to turn this into something of the form an A matrix our A matrix times a C vector, so AC, and we want to say that in some ways this is as close as possible to our y value, or AC minus y is as close as possible to 0. And the problem is we can't actually get 0 here. To do to find the least squares, what we're going to do is, since we can't solve this equation here, we're actually going to solve, well, we can't solve it for two reasons. One is the fact that it has no solution. It is dramatically overdetermined. And so we're going to go to something that actually will have a solution. And I'm not going to go into the details of why this works, other than to say it does. If we multiply, because this is very overdetermined, if we take the transpose of A and we multiply both sides by the transpose of A, this will now become a smaller square matrix, and this will be a vector on the other side that has a matching dimension, so that this is all happy. And it will be something that, assuming that things are linearly independent, is actually going to have a solution to it. Okay, so, and a unique solution. So the question is, well, how do we get our A? The C is pretty obvious. The C is the things that we're trying to solve for, as we saw before with our Gaussian elimination. The y is just a vector of the y values in these points. So what is this A? Well, this A comes from our F there. So the A value at row I, column J, is equal to the ith function, or sorry, the jth function applied to the ith value of x. So each column in A corresponds to a different function, and each row is for a different value of I. And so generally A itself is very non-square. A is going, as I said, we might have like 400 points for 4 equations. So it will have, in that case, it would have 4 columns for the 4 different equations, and then 400 rows for the different points. Note that Y also has 400 rows because it needs to have, we have Y values for every one of those points, so that matches up nicely. We take the transpose of A, multiply it out, and now this is something that we can solve either using, well, we could solve it using Gaussian elimination if we were to code that up, but note that this also can be solved. Your book gives you LUP factorization, and using LUP, or the LUP decomposition, will be much more numerically stable. And so whereas Gaussian elimination could run into problems if your math isn't well behaved, the LUP is going to be better behaved for you. But that same code that if you wrote LUP to solve for a system of equations earlier, you could use that same LUP and simply set your equation up by finding A, doing A transpose A, and then creating A transpose Y as well, and calling that exact same function that you had written previously. So this basically gives you the idea of how you're going to set up for doing a least squares fit using a matrix solver. And that's it for this video.